In the previous part of the lecture, we considered the exponential function y equals e to the x, which is illustrated by the red curve on the axes. Y equals e to the x is a function. It's a one-to-one function, and it has an inverse. The inverse function is a reflection in the line y equals x. If we reflect y equals e to the x in this line, we get the function shown by the yellow curve. This is a very special type of function, and it's called the natural logarithmic function, y equals ln x. We use these symbols ln to indicate that it's the natural logarithmic function. It's special and it's different to other log functions because it's the inverse of the exponential function. The characteristics of the logarithmic function, as it's a reflection in the line y equals x, you can see that it will cut the x-axis at 1. So the natural logarithm of 1, that is ln of 1, will equal 0. As x approaches 0, you can see that the yellow curve decreases in value very rapidly. The y-axis is a vertical asymptote to the natural logarithmic function. And as x approaches positive infinity, y will also approach positive infinity, but quite slowly. The range of the exponential function is y is greater than 0, because the x-axis is a horizontal asymptote to the exponential function. As we know when we find the inverse of a function, the range and the domain are interchanged. So the domain for the natural logarithmic function is x is greater than 0. It's undefined for x equals 0 and cannot take negative values. Having looked at some of the basic properties, let's consider a few transformations of the natural logarithmic function. We'll now look at 3 basic transformations of the natural logarithmic function. And we'll consider the graph of y is equal to a plus b log of cx, where a, b, and c are constants. A represents a vertical translation. B is a vertical scaling, that is a stretch parallel to the y-axis, and c is a horizontal scaling, or a stretch parallel to the x-axis with a scale factor of 1 over c. We'll see what the impact of changing a, b, and c is independently, and we'll be able to see the result in the red text here. Let's start by changing a. We can see that as we increase a, we're translating the graph vertically upwards. And as we would expect, decreasing a, we translate downwards, maintaining the same shape of the graph. Let's set a back to 0. And let's see what effect changing b has. That is, applying a vertical stretch. As b increases, we can see that the graph of the logarithmic function curves upwards more steeply. The shape is changing. But notice that the intercept on the x-axis remains in the same location. It's still intercepting at 1, 0. As we reduce the value of b, when it becomes negative, we'll see that we get a reflection in the x-axis. So when b is negative 1, it's the reflection of log of x in the x-axis. As b becomes more negative, the curve slopes downwards more steeply. We'll set that back to 1. Finally, we'll have a look at the effect of a stretch parallel to the x-axis. As we increase c to 2, our scale factor is a half. So, as we might expect, the curve now cuts the x-axis at a half zero. If we reduce the value of c to a half, our scale factor is 2. And as we can see, it cuts the x-axis at 2, 0. Well, I'm sure we can guess that when c is negative, we'll have a reflection in the y-axis. So, when c is negative 0.5, it's a reflection of the case where c is equal to positive 0.5. We can see that it's cutting the x-axis at minus 2, 0. Obviously, as c is negative, it means we can't have positive values of x, because we can only have a logarithm of a number that's greater than 0. So of course, all of the x values here are negative. Okay, let's go back to the slides then, and we'll look at some problems that we can solve for ourselves. To summarise on what we learned in the animation then, the natural logarithm is written as ln x. Y equals ln x is the inverse of the exponential function y equals e to the x. And ln x is a reflection of the exponential function, or the graph of the exponential function, in the line y equals x. It cuts the x-axis at 1, 0, so log of 1 is 0. As x approaches positive infinity, log of x approaches positive infinity, albeit slowly. And as x approaches 0, log of x approaches negative infinity. Log of x does not exist for x is less than or equal to 0. So in other words, the domain of log of x is greater than 0. The basic transformations we considered were y equals a plus b log of cx. A is a vertical translation, b is a vertical scaling or a stretch, parallel to the y-axis with a scale factor of b, and c is a horizontal scaling with a scale factor of 1 over c. Let's have a look at applying some simple transformations to the logarithmic graph. We'll start with the graph of y equals log of x, and it's illustrated in figure 1 but duplicated in all of the 4 figures so that we can see how each transformation relates to the original graph. We're going to draw the graph of y equals 1 minus log of minus x. We'll start on the second diagram, and we'll sketch on log of minus x. Log of minus x is going to be a reflection in the y-axis, so it will look like this. Y equals log of minus x. In the third diagram, we'll sketch on minus log of minus x. So the curve that we've just drawn in yellow will be reflected in the x-axis. So it's going to look like this. And we should put on minus 1, 0 as the coordinates there, and in the second diagram too. So that's y equals minus log of minus x. In the final figure, we'll translate the graph that we've drawn in figure 3 vertically by 1 unit.
As for the new intersection point, it's easy to find because we will have 1 minus log of minus x is equal to 0. We know that log of e is equal to 1. So the intersection point must be at minus e, 0. And the domain of the function will be x is less than 0. Let's have a look now at a horizontal translation. In the last example, we'll start with y is equal to log of x, and we'll translate it horizontally to y is equal to log of x plus 2. All we have to do is shift the graph 2 units to the left along the x-axis. So the curve will be parallel to log of x, so we'll have the same shape, and the intercept will be minus 1, 0. The domain of this function will be x is greater than negative 2. Now have a go at the multiple choice question.